Welcome to the International Space Station, specifically to the window in the belly of the space station. Now, the view of Earth fills the window. A supply chain connects the station to the Earth like an umbilical cord, providing all the needed air, water, and food. But humans have been farther than low Earth orbit. Let's take a trip to the moon. So 12 people have set their feet on the surface of the moon, and NASA plans to add 8 more before the end of the decade. As part of those plans, there will be some manufacture and production of the food that those astronauts need actually on the surface of the moon. Let's keep going to Mars. Now, Earth is a tiny speck in the Martian sky. If all of your food came from that far-off planet, that would be a pretty precarious position. If there was challenges to that spaceflight delivering whatever you need, or there was changes in the political will on Earth, that would compromise that Earth-Mars supply chain. So human missions are looking at how to distribute manufacturing to places as austere as low Earth orbit, the moon, and also Mars. And if we can do it there, then we can do it here in communities on Earth. The point of my message today is to decentralize the means of production, to relax our dependence on global supply chains, and to stimulate local economies with bespoke ground-up innovation and local productions for the basic needs of human life. The Human Space Program has conducted an audit of what those basic needs are, some technology to make them, and the operations to have them work properly. And just like on Earth, humans need breathable air, nutritious food, drinkable water, and power. The austere lunar environment may seem inhospitable, but it does have the resources to provide much of what is needed. Like, for example, solar radiation can be used to power the grid. It can be used for photosynthesis for agriculture, plants, and algae. And it could also be used as a sterilization technique for waste to control the spread of pathogens. Regolith, or the soil-like material on the moon, contains aluminum and silicon, which can be used to create building blocks, to produce the roadways, maybe the habitation, and the landing pads on the lunar surface. There's also oxides in the regolith, which might be able to be extracted for breathable air. The ices on the moon are a potential source of water. So taken together, there's always a local resource to be utilized. But how do we engage with these resources? To decentralize the production of basic human needs, the answer is the same as on Earth. It's a combination of renewable and non-renewable resources, many of which come from nature. So there's no ecology on the moon. Early astronauts referred to themselves as spam in a can, and partially that self-deprecating moniker came from the idea that the astronauts were put in a sterile environment, in a container even. But every mission to space has taken with it microbes, these stowaways aboard. And the microbes are the seeds for a biome. And so whenever we do go to space, it'll be an ecology that goes with us, not an individual spam in the can. Extreme environments can teach us about how to live in difficult environments. And although I've never been to the surface of the moon, I have been to the South Shetland Islands in Antarctica. And this is a place where during the winter there is darkness, there is sub-freezing conditions. Anything above the water level is going to have to use a hibernation strategy of sorts. But in the summertime, we get above freezing, it thaws, and there's UV radiation and sunlight to propel a whole host of processes. And let's look at a tide pool in Antarctica in the summer. These green spheres swarming around the plant debris in the center, these are green algae, and they are the photosynthetic base of the food web. The algae is eaten by this gliding creature that scans and slides, and it's no bigger than the width of your fingernail. Keep watching to see the stretching motion followed by a scrunch. That's a rotifer, which is exploring between the islands of plant debris. And as the snow melts, these springtails crawl out of the ice. The final thrashing motion brings our attention to this larval krill, which is eaten by the humpback whale. And that migrates from the poles to the tropical regions. And the whale will actually feed in the polar region and then move to the tropics for breeding. And so the abundance of the Arctic environment, of the Antarctic environment, actually fuels her trip across the planet. The organisms in the tide pool use resources from their environment, like sunlight, to establish a food web. And the ability to self-serve their food and clean their water establishes local stability. And that becomes a force of creation that includes the consciousness of the whale. So do you see the parallels between the crew on the moon and the tide pool? If the crew on the moon has reliable access to their basic needs, then they are not just the recipient of deliveries, they become the creators of information. And they do create. They create science. They send back information like pictures of Earth rises from the lunar surface. So what I want to say is that you are more than a delivery address. If people can provide their own basic needs, then the pressure and the imperative to work a job you don't like for someone you don't respect is lessened. So we provide this local autonomy to be able to pursue those aspirations of greater consciousness. Biological resources have historically been foraged, and this is a video of a bioprinter, which was originally designed for regenerative medicine, to build models of human tissue. In the video, the living cells are deposited layer by layer to mimic the anatomy of human tissue. So for example, in cardiac tissue, which is made up of muscle cells and nerve cells and the cells that line your veins and your arteries, you could suspend inks of each of those cells, understanding their arrangement, actually build a tissue that looks like that. And in that construction, you establish the initial momentum, the push, for those cells to behave in a synchronized, coordinated function, and therefore behave as, say, heart. Well, this same technology has been pivoted to use to not just make tissues in a lab, but to make materials like meat or even leather. And that means that we can take a step away from harvesting these goods from the environment and make them without depleting natural environments. So why decentralize the production of basic human needs? Well, let's go through an example to provide medicine for astronauts. Let's pack our medical kit for a trip to Mars. All right, so no one has conducted a deep space mission to say, but current spaceflight doctors plan on prescribing medications that would boost the immune system after a radiation exposure. And that immune-boosting drug is called granulocyte colony-stimulating factor. I'll just refer to it as the immune-boosting drug. The problem is that that radiation medication, which is prescribed today for chemotherapy patients after radiation, that medication has a shelf life of 1 year, and the trip to Mars is 3 to 5. So instead of packing that medication, I'm part of an interdisciplinary team that's looking to create an astropharmacy. And that would mean making the drug in space instead of bringing it. What that involves is the same technology we saw in the Antarctic tide pool. Remember how I said that the life can tolerate that extended dormancy of the winter? Well, life has evolved all kinds of adaptations to hostile environments, including radiation and dehydration, the kind of conditions we'd expect on that mission. So the idea is to package the drug in this extremely stable storage system in life. And this immune-boosting drug is a protein-based drug, meaning it can be made biologically. So the idea is we formulate the microbes using a combination of using synthetic biology. We formulate the microbes to produce the target drug. We pack them as spores in a form similar to similar to baker's yeast, and then hydrate them during the mission when we need them. Like for example, there could be a radiation event that was not expected. A dosimeter on the outside of the station detects that anomaly and then automatically initiates a process to hydrate the spores and produce the drug. So it's available in a matter of days instead of being several years old from the Earth. Now for a far future vision. Instead of packing the drugs from Earth or having formulated them from Earth, update the drug formula similar to how you update your computer code. We can translate genetic code to digital files due to cataloging efforts from projects like the Human Genome Project. The digital information can be shared between Mars and Earth in a matter of minutes at the speed of light. The Martian crew can reformulate the drugs from downloads from email attachments, and then, pending technological advancements, actually download that formula into the microbe itself. So medicine can be treated as code and not cargo. Local production of biology for basic human needs, like the immune-boosting drug, are made more accessible through shared information. With quality controls, this can be a gateway to open-source medicine. So let's close by going back to the space station. This flower was brought up from the Earth as a seed and grown on the station. Given all it needs, soil, sunlight, water, the seed is the code and the flower is the cargo. So now we have the tools to decentralize the means of production. Let's get to work. Thank you.